go live on Instagram.
Go.
Go on to learn some calculus.
Yeah. All right. So section 2.5 is the fundamental theorem of algebra. Okay, the fundamental theorem of algebra. Algebra was a big deal. It was a big deal when it first came out. Okay. It's what we call an existence theorem. It tells us something exists, but it doesn't help us find it. Okay? It says, hey, yeah, this is out there. We have no idea how to find them all, but it's there. Okay, so it's what we call an existence theorem. So we know so far that an nth degree polynomial can have at most n real zeros, right? If we have something to the fifth power, we know at most it can have 5 zeros, right? Okay. In the complex number system, the statement can be improved. Now that we've dealt with our I, now that we have our complex numbers, every nth degree polynomial not only can have at most n real zeros, now we know it has precisely n zeros. Meaning, if I have something x to the 6th, it has how many zeros? 6. We know it has exactly 6, but that counts the multiplicity, right? Something can count for more than 1. Okay, this important result was derived in the fundamental theorem of algebra. This was first proved by the German mathematician Carl Friedrich Gauss, which, when it comes to mathematicians and actually looking at the life of some of these mathematicians, his was very interesting. So he definitely was not a boring mathematician. He was basically kind of one of those child prodigies, but he was really obnoxious about it.
What do you mean?
Meaning, he drove his teachers nuts, because he wasn't the type to just sit and listen to stuff he already knew. So his teachers always had to find ways to keep him busy by giving him puzzles and things to do, things that they thought would take him hours, and he'd turn it out in 10 minutes and drive him completely insane, because they couldn't keep him
Could
busy.
you imagine how, like, as a teacher, wouldn't that make you just feel so dumb? Like,
And to have a student who, like, almost knows more than you, or knows more than you,
so you have to find things for him to do.
and to challenge him, because if he's not challenged, he's going to cause issues in class,
Yeah.
right? So yeah, but he actually came up with this one. He actually proved it. We know in mathematics we can't do anything if it just looks like it. We have to have a formal proof. It has to be proven. So this is a theorem, so what does that tell me? Theorem, back in geometry. It's been proven. It can be proven, it's been proven. Okay, so if a polynomial of degree n, where n is greater than 0, then n has at least 1 0 in the complex number system. So this tells us that every polynomial can be solved. Every single polynomial on the planet has at least one solution. Okay? So what he was able to prove, and I honestly have never even looked in depth at the proof of this, but what he was able to prove is that every polynomial can be solved. The solutions, see, that's the thing, is was he able to write every single one? No. So the proof was not what we call an exhaustive proof, where he proved it by proving every single polynomial can be, no, he didn't. It wasn't an exhaustive proof where he proved it for all cases. Because is that possible? No. That's not even possible. Okay, so he must have had a general proof somehow, that somehow in his proof he was able to prove every polynomial could be solved. Okay, and not only could it be solved, but we know that it has to have precisely n linear factors, meaning that if it's x to the 5th, I can write it as 5 factors, right? Some of them might not be real, right? Some of them could be imaginary. They all could be imaginary. None of them might be real, okay? But we know that we can factor everything down, okay? So the first few examples in our book has us actually writing out, like just proving that something is a 0, or that it's a factor. How would we do that? Like example 1 in our book. We're just going to look at the example. We're not going to work through the whole thing, so we don't have time to do it. Okay, so it says counting multiplicities. Confirm that the secondary polynomial function has exactly 2 zeros, 3 and 3, meaning it occurs twice. So what they did is they just factored this guy. This factors into x minus 3 squared. So that means x minus 3 is a 0 twice, because there's 2 of them. Another way you could have done this is to prove that it has exactly 2 zeros. I could have synthetically divided by 3. and then synthetically divide it again by 3. Okay? There's a lot of different ways of doing this, okay, to prove that it has exactly 2 zeros. And we know it has to have exactly 2 because it's x squared. And this 3 counts as 2 of them, right? Because it happens twice. Okay, that multiplicity idea. That's just confirming that something is a 0. What we're going to be spending a lot of our time with is actually finding them. Okay, that's an example. Another way of proving is example 2. We'll work out example 2 just because one of them is imaginary. Okay. Example 2, they give us a polynomial function. F of x equals x to the third plus 4x. So how many zeros does this guy have? 3. It's x to the third. So we know it has to have 3, but it says confirm that its zeros are x equals 0, x equals 2i, and x equals negative 2i. So they give me the 3 zeros, right? Okay, well I could plug in all 3 of them and make sure I get 0. Well, the first one isn't hard to plug in, right? I don't know about you, but I don't want to do that much. But I could plug in the 2i. Take 2i to the third plus 4i. Okay. But another way I can do it is if these are giving me my zeros, I can write the factors. So this would be, my factor here would be x, right? This one would be x minus 2i, right? Subtract the 2i over. And this one would be x plus 2i. Multiply it out. What should I get when I'm multiplying?
X cubed
Plus
plus
4x. So to make life easier on myself to multiply, you multiply 2 things at a time, right? I'm going to multiply these 2 first. Why would I pick the 2 most complicated
Because
things to multiply?
it'll be easier to multiply them two before you put the x squared.
Yes. And what do we call these 2? Do you guys know this? We have x minus 2i, x plus 2i.
Polynomials.
Conjugates, thank you, Zai. They are polynomials, actually binomials, 2 terms. They're conjugates because 1 plus is 1 minus. So when I multiply this guy out, I'll have what? X squared plus 2ix minus 2yx minus
4i squared. Which would be plus 4. So x squared plus.
So these add out. I'm left with x squared plus 4.
Yes.
And then I have to multiply it out front by that x. X cubed plus 4x.
Yeah.
Yay, it matched where we started. So we verified, yes, that those are the 3 zeros.
So that's what we do.
Yeah, confirm it.
That is.
That's one way. Is that the only way to confirm that these are zeros?
Absolutely.
No.
No.
No. You
Is there
could
an
put
easier
each one
way
of them
or a
in.
harder way?
Not really. It kind of depends on you, which way you think is easier. Another way is I can plug them all in. I can try f of 0, f of 2i, f of
That
negative
sounds
2i.
really complicated.
What should I get out for all of these?
0.
0. Check to make sure that that actually works. Plug them all in. But I have to plug in 3 different things.
Yeah.
I'm gonna have 5 zeros and I'm plugging 5
If we
different
could
things.
plug in
No.
an I into the calculator, we could do that.
Another way is you could synthetically divide
That's what I was thinking.
Ooh.
and check your remainder here should be double check, make sure you get a 0 there.
So you synthetically
But-
divide 3 times.
Yeah, I'd have to synthetically divide 3 times. And I'd have to synthetically divide by 2i.
We'll skip.
Yeah.
We'll stick with option number 1 unless there's easier
Yeah, that
ways.
would stuff with the I.
Okay, so yeah, to me that first option is just a strict multiply, right? You write the factors and multiply it out. We're all pretty good multipliers by now.
What 9 times?
Okay. All right, let's go ahead and let's do example 3. Look over the end. Okay, so it says write f of x equals x to the 5th plus x to the 3rd plus 2x squared minus 12x plus 8.
Oh my gosh.
As a product of linear factors and list all the zeros. So meaning, first, if I want to write it as a product of linear factors, basically they want me to do this to it. Like on that last one, right? How many factors should this have?
5.
5. Should have 5 of them. So to help me find those 5 linear factors, I'm going to find the 5 zeros on this. Okay, so where should I start? Does a factor easily?
With
It's
a
got 1, 2, 3, 4, 5 terms. No.
division.
Could I use a quadratic formula?
Yes. No, not
It's
yet.
not quadratic. So no, it's x to the fifth. Okay, so I'm gonna go to my p's over q's, just to get a list of possible zeros, and then I'm gonna use my calculator to find,
So,
Find
8
them.
over 1.
so this would be 1 and 8 and 2 and 4, right? Oh, this is nice, that's just 1 and 1, right?
Yep.
So we'll have, what?
Plus
One,
minus
2,
Or not three,
4, and 8,
4.
right? Okay, so we wanna see which one of those work, right? Okay, calculator, help me out, I don't want to synthetically divide by everything, right?
Yeah.
So we're gonna what equals x to the fifth plus x to the third plus 2x squared minus 12x plus 8.
And then you table it, and then you point them.
Go to my table and let's plug them in. 1 worked, hey. First try, 1 worked, so I'm synthetically divide by 1. So what do we got? 1, 0, 1, 2, negative 12, 8.
Remainder is 0.
We should have a remainder 0.
Well, I thought you were gonna put it right
1,
over
1, we've got 1, 1, 1, 2, 2, 4, 4, negative 8, 8, 0. Okay, so 1 worked. Let's try negative 1. Nope. 2, negative 2. Negative 2 worked. So I'm going to synthetically divide again by negative 2. And that original
So
one.
1, negative 2, negative 1.
2, 4, negative 8, negative 4, 8. Okay, am I down to quadratic yet?
Nope, one more.
No? Okay, so let's see what else. So I tried negative 2, 4, negative 4, 8, negative 8. None of the rest of them work.
That's impossible.
No, not impossible. Imaginary.
So we found 2 real ones so far, right?
Couldn't you just like split?
Could we
it?
try 1 and 2, negative 2 again? Maybe one of them will go, maybe one of them's got a multiplicity of 2.
Oh, yeah.
Maybe.
So should we try it again?
One,
I'm gonna do
try
this one in
one.
red because we don't know for sure if it'll work, but let's try it.
I think
One.
one will work, because there's a 4.
0, 0, 4.
Yep. Nope, nope, yeah.
Okay, so 1 worked twice. So far my zeros are x equals 1, x equals negative 2, x equals 1, and then we have x squared plus
Plus 4.
4 equals 0. We need 2 more, we've got 3. So x squared,
Quadratic.
so,
So
oh,
it's
I
gonna
don't even need a quadratic.
It's gonna be 2i.
X squared equals negative 4, square root both sides.
2i.
Plus or minus 2i.
Yes.
So we found them all. So it says we want me to list the factors. So my factors would be what? X minus 1, x minus 1. We've got 2 of those, right?
X plus 2.
X plus 2,
X minus
X
2i.
minus 2i. And
X
x
plus
plus
2i.
2i.
do I have all 5 factors?
So smart.
Yep, and then now all my zeros would be 1,
1.
Negative 2, positive 2i,
and
negative
plus or minus 2i.
Yeah.
And we should probably mark this has a
Two.
multiplicity of,
Yeah.
Oh.
so that shows that I've got all 5 of them, right? I need to list the multiplicities. If you're not going to list this multiplicity of 2 down there, then you need to list them both. 1, 1, negative 2, 2i, negative 2i. So we found all 5 and we factored it.
Ladies and gentlemen, we got it.
You got it? All right, so in between now and tomorrow, it would be awesome if you got started on some of these practice problems. For the most part, these beginning ones should go really fast. So page 144, get started on possibly 2 through
54. Just kidding.
probably 14, maybe through 16 to evens. It'd be awesome if you got to start. That's how many problems? 8. 8.
Well, it's not bad.
Oh my god, I didn't sleep.
No, I think I might consider it.
So 8 problems. It would be awesome if you got started on those 8 before tomorrow, but guys, if you don't have time, you don't have time.